Everyone. Thank you for attending the meeting. I think this is the first time we had like after a month, like usually we have every 2 weeks. It's a long gap this time. This time we have Professor Keh-Chyuan Tsai. I'm sorry if I am pronouncing it wrong. He's a professor at NTU, National Taiwan University, and they organized a blind prediction for a complex structure on E-shake table defense, and today they are going to present the modeling and also the results from that. Professor and his team will be talking about it, and it's all yours now.
Okay, thank you, Pavan. First, I'd like to express my appreciation to the OpenSeas support group, for inviting me and my colleagues to attend this meeting. And this team, of course, include a graduate student, Mr. Ye-Ying Tsai, and two colleagues of mine in National Center for Research on Earthquake Engineering, Dr. Mingjie Zhuang and Dr. Ruiliang Lin. And so all four of us are very excited about this meeting. And I want to do a little bit more introduction about Ye-Ying. The key speaker will be Mr. Ye-Ying Tsai. He now is a graduate student at our Structural Engineering Division of Civil Engineering Department at NTU. And he has done his undergraduate in NTU also. And he has done 2 years of master study in our division. And in fact, he is now in the United States in California. He's heading for Texas A&M for the International Student Exchange Program, and he's going to stay there for 1 year. And so he had the chance to take part in this blind prediction contest starting from sometime last year. But this activity is not his key master thesis study. His master thesis study is on the optimization of some damper systems using cloud computing. So I have done pretty much the introduction I like to do about Mr. Ye-Ying Tsai. So I like to give the speaking to Ye-Ying Ye-Ying.
Okay, thanks Professor Tsai's introduction, and thanks the OpenSeas group meeting for that chance to give the presentation here, and thanks Professor Pavan. Okay.
I'm not a professor, sorry, I'm still a student.
Okay, thank you. Let me share the PowerPoint.
Oh, perfect. Okay.
Okay, good morning, everyone. I'm Ye-Ying Tsai, and my advisor is Keh-Chyuan Tsai, professor in NTU, and Mingjie Zhuang and Ruiliang Lin, both are research in National Center for Research on Earthquake Engineering. And it's my honor to present in the meeting here. In today's OpenSeas meeting, I will talk about the modeling and blind response prediction of a complex structure on E-defense shaking table. Last year, the blind prediction contest was held in Japan, and our team participated in the contest using OpenSeas. And we got first place in the structure prediction. So today, I will present about this topic. Okay. In the presentation, I will first introduce what is blind prediction contest, then the numerical modeling of the specimen. Then I will show the result of modeling and compare the analysis result with the experiment result. And the last is the summary. Okay, that is the 2020 blind prediction context. In the past decades, many full-scale buildings were tested on the e-defense shaking table. The blind prediction contests were held for several times. In the context, the contestants were invited to predict the specified structural response using the input ground motion. In 2007, a four-story moment-resisting frame was shaken to collapse. And in 2009, a five-story frame with BRBF and viscous damper frame was tested. And 2011, a five-story was tested with a different base configuration, fixed base and base isolated. Then in the last year, 2020, a complex structure of combined with the four-story fixed base building and the three-story base isolated building was tested. And the team from ANCRI and NTU has participated in the contest for several times. In 2007, we got first place in 3D category using OpenSys, and the second place in 2D category using PISA 3D. The PISA 3D is the platform of inelastic structure analysis for 3D system, which is developed by NTU and ANCRI. And in 2009 and 2011, we also got great results using OpenSys and PISA 3D. Then in the last year, we got first place in structure response using OpenSys. Let me first introduce our team member, but I have Professor Tsai has introduced in the last time. I'm Yan Zhan, a graduate research assistant, and Dr. Keh-Chyuan Tsai, professor in NTU, and Mingjie Zhuang, researcher in ANCRI, and Dr. Guiliang Lin, research fellow in ANCRI. Okay, let's see the specimen in the 2020 BPC. The specimen consists of two buildings. One is the fixed base building, and the other one is base isolated building. The below is the floor plan of specimen. The XY direction is defined like this, not like the normal one, are defined according to the context regulation. Okay, there are three categories in the context. One is the structural response prediction. There are 5 items for fixed base building, including floor acceleration, story drift, beam end rotation, and the column base rotation, and the relative displacement of the expansion joint. And 2 items in the isolated building. One is floor acceleration, and the other is displacement of isolator. The other category is non-structural response, including piping, tank, and the light. And the third category is still non-structural response, but using the structural response after the experiment. In these 3 categories, we participate in the structural response, which is the most number of teams competing in. In the score counting, there are two parts. One is submission score, and the other is accuracy score. Below is the table of our score, and we got 21 submission score and 20 accuracy score, and got first place in 18 teams. Okay, let's see the numerical modeling. Okay, this is a summary of numerical modeling. My software for analysis the model is using the OpenSys, and the GUI for building model is GID plus open seats. In the numerical procedure, I adopt a numeric integration with gamma 0.5 and beta 0.25. And P delta is adopted for geometry transformation. And Newton line search is used for solver algorithm. And integration time step size is 0.005 seconds. And 1% damping applied for first and the sixth mode of fixed space building in computing Rayleigh damping. Then in the numerical model, risk floor diaphragm is assumed for all floors. And the total depth load for each floor provided by organizer is adopted. And mass are placed at the column center lines considering the distributary area of the columns. And all line elements in the numerical model are forced beam column with 3 integration points. Okay. This is the schematic of a numerical model. Okay. You can see the blue line in the corner of beam and column. These are the read bar for simulate the panel zone. And the pink line in the third floor of the fixed space building is to simulate the exterior diaphragm, which cannot be seen clearly. And the gray line, are the gray beams with elastic section. And the joint between the column and the gray line are the zero length element to simulate the ductile column base, which is spatial in this context. Then the yellow line is composite beam, which is used the fiber section. And the column are also used fiber section. The last is the isolator. I use triple friction pendulum to simulate the isolated building. Okay. This page shows the some location of nodes to notice and the mass as elevation in numerical model. The mass is placed at the 50 millimeters above the top of the beam as the average height by weight of concrete floor and the weight of the steel structure. And the column nodes, this node at the top of the beams and the bottom of the beams and at the column base are to simulate the panel zone. And at the bottom of the isolator, one node is fixed at the 0 millimeters height at the shaking table and 330 millimeters height and plus 157 height are the lower nodes and the upper nodes of the isolator. Then in the second floor of the big space building, the context organizer placed 2 LVDT to measure the rotation of the beam. So I also placed a node 1,500 meters away from the column base to measure the rotation of the beams. I use the rotation in the node I here minus the rotation in the node J here to get the this rotation of these beams. Finally, in the column base of big space building, there are nodes at the 0 millimeters high at the fixed at the shaking table, and the 1,050 millimeters high of the column base, which is 50 millimeters high above the first floor because of the cement of the ductile column base. And between these 2 nodes, one node is put in the middle to connect the great beams. Okay, let's see the column base in the fixed space building. This is the high base echo made by Keh-Chyuan in Japan. When sustaining bending, this ductile column base is designed to make the bolt yielding prior to the column base. So the moment rotation diagram of the column base is like this provided by the organizer. The loading and unloading history will like this. The bolt will yielding prior to the column base. Okay. This is the top view of the column base. The estimated yield moment can be calculated by this equation. The bolt can give the moment to the column base, and the number of this moment yielding moment are matched to a certain degree to the figure. Then let's see the in the numerical model. I use zero length element in the numerical model, and in the Rx and Ry degree of freedom of the zero length element, I use self-centering material to simulate the ductile behavior. The one node I is connected to the grid beam, and the other node J is connected to column. Then between these two nodes, the zero length element is adopted, and the Rx, Ry, two horizontal rotation degree of freedom is your self-centering material. Then the simulated results are like this, red line. These are matched to a certain degree to experiment data. Then let's see the panel zone. When the panel zone sustaining bending moment, the shear deformation occurs like this. So to model the behavior of panel zone, the nodes are placed at the four edge of the panel zone. Within these nodes, the ridge bar are connected within the panel zone. And in the center of the panel zone, there are two nodes. Here is the schematic, node I and node J. Node I is connected to the things, and node J is connected to the column. Between node I and node J, there is zero length element. And in the Rx and Ry degree of freedom, still 0,1 material for hardening to stimulate the rotational stiffness and the deformation of the panel zone. And the other 4 degrees of freedom are tied together. The rotational stiffness of the panel zone and the yielding capacity can be calculated by these formulas in the Tsai and the Popov 1990s. Okay, let's see the through and the exterior diaphragm. In normal floors, through diaphragm to connect the beam moment to columns are used like this. But in the third floor of fixed space building, there are exterior diaphragm. The organizer provides the experiment data of through and the exterior diaphragm. The experiment setting is like this. The columns are placed parallel to the ground, and the column and the beam connect to the columns. The moment and the rotation diaphragm are like this. The blue one is through diaphragm, and the orange one is exterior diaphragm. We can see the orange line is the yielding moment of origin line is a little higher than the blue line. So in the numerical model, I put the nodes at the edge of the exterior diaphragm. Then the width of the bins between these and these two nodes are calibrated to make the behavior are similar to the experiment data, origin line. Okay. Then is the composite bin. For modeling the composite bin, fiber section is used. The upper white part is concrete part, and the lower gray part is steel beams. The deck on the floor is like this. There is no gap in the lower part of the deck, so the beam perpendicular to slab and the beam parallel to slab has the full height of the effective compressive area. So both the beam parallel to slab and the perpendicular to slab has the height of 150 millimeters of height, and the width is the 300 millimeters. The 300 millimeters width is adapted from the past concave experiment, Yu et al. In 2010. The concrete 4 material is adapted for the concrete material. Then the remaining is number of fibers, Young's modules, and the strength, and the crushing point is this here. Then the dimension of steel beam is set according to real dimension provided by organizer. The steel 01 material with 4% hardening rate is used. Then the number of fiber is 7 layers, and Young's modules and yielding strength and hardening ratio is 4.4%. Okay, the final part in the numerical modeling is double concave friction pendulum system. According to manufacturer, Nippon Steel Engineering, the isolator has 0.013 of friction coefficient, and the radius of sliding curvature is 4.5 meters, and the period is 6 seconds. By the following equation from Vance and the Constantino in 2006, we can calculate the period. The period is equal to 2 pi times square root of equivalent of radius divided by g. And the equivalent radius is equal to the sliding radius of upper plate plus the radius of lower plate. And the result is 6 seconds. That is matched to the information from the manufacturer. Then in the open seas, there is no certain element for the double concave isolator. So I use triple friction pendulum to simulate. To catch the behavior of the double concave pendulum, the friction of inner sliding surface, the red line here, is set big enough to prevent slider from sliding. So I use Coulomb friction model and set friction coefficient of inner sliding surface as 1.0. It is big enough from sliding. And the outer sliding surface is 0.013 as the manufacturer information. Okay. Let's see the analysis result. Okay. The first is model analysis. The first 3 mode of building F, fixed space building, is like this. In y direction, 0.75. In x direction, 0.68. And in rotation z is 0.649. And the first three modes of building I base isolated are like this. The first three modes are all 6 seconds in x, y, yx, and the rotation z. Okay, let's see the improved ground motion. There are 3 ground motion in the context. First ground motion is Kobe 50% x, and the second ground motion is OS2 50% in x and y direction. And the third ground motion is Kobe 50% in x and y direction, and the Kobe 100% in z direction. This is the 1% damping spectrum of this ground motion. Because the organizer conduct the experiment in series, the specimen will be affected by previous ground motion. So the improved ground motion are lined up one after one in analysis. So the final improved ground motion in the numerical model will like this, x, y, and z. Okay. Here is the peak floor displacement. The peak displacement of the roof of fixed space building is 150 meters in x direction. And the response in y direction are larger than the x direction because there are only one bay in y direction. For isolated building, the whole floors almost move together. So the peak displacement of each floor are close. Okay. Here is the peak story drift. For fixed space building, in the third ground motion, green line in the picture, the first story drift in y direction is large because the ductile column base occurs a large rotation in this ground motion. And there is a little story drift in base isolated building. So the dashed line is the base isolated building information. There is a few story drift. Okay. Then this is the peak acceleration. For the fixed space building, the hard line, the peak acceleration of the roof are over 10 meters per second square. And for base isolated building, the acceleration of each floor are less than 5 meters per second square. Okay. And we will go to analysis result compared to the experiment result. This is the isolator displacement history provided by context organizer. The blue line is the experiment result, and the orange line is our prediction. Two lines in the 3 input ground motion are matched closely. Okay. This is the relative displacement of two buildings. The time of the nearest displacement occurred in the second ground motion, OS2, in the red square here. Here is the animation of the analysis. You can see the gap not collide together. The gap between two buildings are designed as 600 meters, and the maximum relative displacement in y direction is 235 millimeters. So the two buildings will not collide together in the experiment. And we can see the test data and the prediction data match well. Okay. This is the comparison of the column base in the fixed base building. The left-hand side is the analysis result, and the right-hand side is test result. In each figure, left column is X direction, and the right column is Y direction. The first row is first ground motion, and second row is and the second row is the second input ground motion, and so on. We can see the behavior of analysis and the test are similar. This is the comparison of the beam and rotation. The Y direction of the test result are not available, so the organizer only provides X result. And we can see the peak value are close in X direction and in X direction. Okay, this is a summary of our analysis versus experiment result. Some are very close, like 2% or 0.9%, but some are differs large. This can be studied in the near future. Summary. The prediction result shows a well agreement with the test result, and the triple friction pendulum element can simulate the double concave pendulum read well by elaborated modeling. The zero length element is used to simulate ductile column base behavior and the panel zone deformation. The material nodes, the material model of zero length element for the column base can be further studied in the near future. And this is all reference in this PowerPoint. And the OpenSys program developed by Dr. Frank McKenna and other research at Peer Center and the UC Berkeley is very much appreciated. And part of the present research is supported by Tokyo Metropolitan Resilience Project of the National Research Institute for Earth Science and Disaster Resilience. The organizers are gratefully appreciated for organizing the blind prediction contest, conducting the test and sharing the test result. And this study is supported by Ministry of Science and Technology, Taiwan RC. And thank you for your attention. Thanks.
Thank you, Yeying, for your presentation. Sorry, yeah. So thank you for your presentation and your modeling, and I hope it will help everyone how to model the fine elements connections well. Any questions from anyone in the audience? Please feel free to ask any questions. I mean, I can ask a couple of questions if by the time others ask. So one thing is in your acceleration response spectrum, you use 1% damping. Is there a reason for that?
Yes.
I don't remember the slide number, sorry.
That's no problem. Yes, because we consider the first to 6 mode of the fixed building is important in our analysis. So, and 2% may be too big for the damping, but so we use 1% in our numerical model. So we apply 1% damping in the spectrum analysis, same as the 1% damping in our numerical model.
No, my question was like, how did you come up with 1%? Like, because I didn't understand, sorry, your answer. So you can usually for structures, the code recommends are like 3%, 4%, 5%, depending on the structure, right? And the connections you're using and everything. So I was just curious how you came up with 1%, because for the modeling, first there is the experimental, you have certain amount of damping in the experimental, and this 1% is rally damping is in addition to the hysteretic damping and all that, because you're using a lot of elastic sections, elastic members also. So I was thinking 1% was a little low because you're replacing a lot of rigid connections and elastic sections. So I was just curious.
Okay.
Yeah, I may be able to help. I think this 1% damping applied on the first and the sixth modes of the fixed-based structure is very much under my suggestion.
Okay.
And the reason of using 1% is because we figure there are various levels of shaking. So in the beginning of the contest, I think they will use low level of shaking. So I figure maybe 2% damping would be too obvious. I think 1% damping may be fine. And then the reason we apply on the first and the sixth, we figure because the first several modes are closely coupled. They are very similar. They are very similar period. So this 1% damping applied on first and sixth is rather is somehow arbitrary, I would say.
Okay.
And so it could have been higher, say 1.5% or even 2%, and applied on first and second mode, and the result could be even improved. I don't know. We will, I guess, try to see the result if we increase the damping to see if the accuracy will be improved or not. So it was somehow arbitrary. Yeah, kind of.
And not only on this, like on the acceleration response spectrum plots he has, there was 1% used there also.
Yeah, that's just for the comparison purpose, because he applied 1% in his structural model, so we figure it's better to show the 1% damped response spectra.
Okay. And also, when you are showing the errors between the test and the model, experimental and the model, you got like very close to the global response, like the parameters close to the global response, and you got like high error in the localized parameters. That's what I didn't notice all the parameters, but like couple of them were like localized parameters. Is there a reason for that? Like you are focusing more on the global response than for the blind prediction, they are expecting only the global parameters, or like even at the local parameters they are focusing? I was just curious to know that. In the last slides, the errors.
Can you go to that last page showing the table showing all the
errors? Yes.
Errors. The table. Yeah,
yes.
This one.
I was just curious, like you have like error higher for like plastic rotations, which is localized, right? Like local errors. And for the story drift, which is the global response, you have like very less error. I mean, I understand you can capture either global or local. Is there a reason for capturing better the global response than the local response? Am I clear?
Maybe I can help. I think
Yeah.
the table shows the various errors in terms of percentage on a number of response parameters. And I guess some of the error in terms of ratio is very high. I guess it's because if the denominator is small, and then if you have a huge, you have a slight large numerator, then you will get a large error ratio. So I guess this large error ratio may not mean a very significant error, or it would not have significant impact on the more overall response of the structure. For example, when I say overall response means flow displacement or interstory drift of response parameter of that nature. So in terms of local, for example, the plastic rotation of column base, you can see they have shown large errors in terms of percentage.
Yes.
So I guess it's because I really don't know this column base plastic component maybe not so big measured from the experiment, and maybe it's because the denominator is not very large. And then once you have some error, and then the ratio will be high.
Okay.
For example. And so if we look at the story drift, for example, of the first story, so the accuracy is satisfactory. But at the same time, the first story drift is very much depend on the column-based rotation. So I really don't know why the first story drift shows good accuracy, but at the same time, the plastic rotation of the column base, it's in great error, and that's something we should look into further, perhaps.
Okay, cool. Yeah, I was just curious, like how serious were those numbers? Okay. Any other questions from anyone?
Hello, Professor and Inja. Thank you for the nice presentation. Amazing job. I have a question about, in general, when we do our modeling, we have the test result. And for this blind contest, you do not have the test result. And as we do, we build the model, the material parameters is sometimes, I think, according to my experience, is sensitive to the modeling results, especially for the concrete parameter and the steel parameter for the stress and strain value. How can you choose those values for the modeling? Just according to your experience or something else?
Thank you for your question. I can answer this question.
Yeah, you may want to go to the table showing all the material. Yeah.
For example, this Young's modules and the strength and the crushing point are determined by the suggestion in the OpenSys wiki, and this Young's module is provided by the organizer of the context for the concrete part. And for the steel beam, there are coupon tests for many beams, like the flange and the web of the beams. So the Young's modules are used, provided by the organizer. And 4% hardening ratio is to calibrate from the experiment data. And this experiment data are given by the organizer. So we calibrate it to get a 4% hardening ratio.
Okay, thank you. As those values were provided by the organizer or some material, is that the key point for this modeling is not about how to choose the material, is about how to model the certain elements of the structure. Is that right?
Yes, I think it's more important to choose the element and the numerical setting rather than this material number.
Okay, thank you, understood. Thank you very much.
May I add some more comments?
Yes, please.
Okay, I think thank you for the question, and thank Ye-Ying for the answer. And I think what we are doing here, of course, is trying to use whatever the information provided by the organizer on the material strength. So as pointed out, coupon strength has been used, and the coupon strengths have been provided by the organizers. And I think Ye-Ying has taken the average of the beam web and the beam flange and used the same averaged yield stress for the steel beam. But I want to say something about the width of the composite beam section of the concrete slab. We have decided to use 300 millimeter to represent the effective width of the concrete slab. But in fact, if you follow various kind of design code, you would find the effective width of the concrete slab is very much dependent on the span. And if you follow the recommendation, you would probably come up different effective widths for the spandrel beam, and you will have a bigger equivalent effective width for the beam that has slab on both sides of the beam. But we have here chosen 300 millimeter. It's because I think this effective width of the concrete slab is also very much dependent on the beam depth to the concrete slab thickness ratio. I think that if you have a very deep beam, very strong beam, I think you will be able to drive a wider effective width of the concrete slab, even of the same given span. And so this 300 millimeter effective width is very much coming from the experience we had in the previous blind precision contest, because the steel beam is very much similar to the specimens the beam specimen in the building tested previously. So for this reason, of course, the beam is relatively small comparing with the actual tall buildings, and therefore this 300 millimeter width of effective slab is very much smaller than what you would get from the building code provisions. And Ye-Ying, you may want to go to the location of center of mass.
Location center.
And I may also want to say some words about the location of the center of the mass. So this again is an approximation to try to catch the discrete model where that the center of mass may be, the elevation location may be important. So we have decided to, try our best to say it's not at the center of the beam, of course, because concrete slab would have contributed more weight than the steel structure. And so we kind of approximately assume the center of mass is slightly above the top of steel beam, and slightly below the center of the thickness of the concrete slab. So the concrete slab is 150 millimeters thick, and the center of mass is assumed it's only 50 millimeter above the steel beam top flange. So again, this is a approximation, and we really don't know where using this discrete simplified model. We really don't know where is the precise center of mass. And again, using this slide, you can see we want to capture the deformational characteristics at the beam to column joint where panel zone may deform. And so we have used additional nodes and additional rigid bars to capture the rigid and offset. And at the same time, we have used a zero length joint element to simulate the deformational, characteristics of the panel zone. So these are I think they are important and very important and influential techniques, I think, to make sure you have captured the mass and the deformational parts of various members, beams, and columns. You try our best to use fiber elements, and then try our best to add additional nodes at the beam to column intersections. And these are important together with the material property, of course. They are also very important, I think.
Oh, thank you. And another thing is, you told me those beam size, or according to the previous test, is the dimension of those specimen the same as the specimen used in this test, or is there any size effect in it?
You say which specimen is
the column, the beam column, or the beam component or column component used in this test, in this shape taking, is the same size as the previous test?
Yes.
Similar. No, I say the column and beam size are similar to the building specimen test in 2007 or 2011. That's beam and a column of similar size.
Okay, thank you. Thank you very much.
Any other questions from anyone else? Okay, so I have one small, I'm curious with your experience. Can you go to the next slide, please? Next slide where the building you're showing. Next slide. Yeah.
Please.
No, next one, sorry. With the building. So where you have, so I was just curious, like I never modeled a dynamic with a building with all the non-structural components, because like, for example, we have chairs. During the earthquake, chairs and all these things move, right? Like, but we cannot model that stuff in OpenSpace. I was just curious to know, like, how much of that will affect the response of the structure modeling, being able to model that well.
Number of structure.
Yeah, for example, all the chairs and tables, everything can move, right, on the building. So it's a good amount of mass moving too. So relative, I'm not sure. I was just curious to know from your experience, how much of. Sorry guys, we have a fire. Sorry, I have to leave because of the fire thing.
Okay. I think you should leave.
Evacuate the building using the nearest fire exit.
Okay. Sorry.
Okay, it's okay.
Thank you everyone for attending the presentation. Sorry, I have to stop the session.